During this video, I'm going to do a few demonstrations you might like to participate. If you want to participate, you're going to need a glass with water in it, a pencil or a straw that fits inside the glass, and a piece of paper with an arrow drawn on it, dark enough that you'll be able to see it through the glass of water. Pause now and go get those things if you'd like to participate.
Hi everybody, it's Mrs. Kelchner, and I heard someone on the news the other day interviewing a kid who was doing homeschool, and the kid said it is none of the fun parts of school and all of the homework, and that it was really boring. And you know, I was kind of feeling that way too. I get to talk to a few of you each week if you join in on the live lab, but for the most part, I'm not getting to talk to kids, and that's really why I started doing the job. So this is the best I can do, talking to kids. So today I'm going to show you a couple videos, but instead of making the whole lesson you watching videos, you're going to get to see me. Woohoo! Yay! And I get to teach, which is what I love to do. So today we are talking about waves. You've already watched one video or done one activity from Ms. Rary on waves, and specifically about light and sound. What I'm going to talk to you today about is what happens when those waves, once they leave the place that made them, whether it's something you see and the light is traveling towards your eyes, or whether it's a sound and the sound travels out, what happens to those waves? There's a couple different things that can go on, and hopefully some of them you already know, but some of them maybe you'll learn today. Those are my puppies in the background. Sorry, they're puppies. Okay, so the first thing that could happen to a wave is that it could come upon something and just pass right through it. So I'm going to use this star as an example of an incident that made a wave, whether it's the sound of my puppies in the next room or me looking at the leaf outside my window. Something has happened right here. Now, when we talk about waves, I know you've learned about the amplitude and about the crest and the trough. When we call waves what we see at the beach, crashing on the shore, those aren't really waves anymore. What were the waves were the things that were coming, the rollers that were coming in. So imagine if I turned my head this way, I'd have up, down, up, down, up, down. And so this is like if you dropped a pebble in a pond and the waves rippled out from that. We could say each of these lines is the crest. It could also be the trough. It doesn't really matter. But they're going out this direction. Remember, they're also going in that direction, and that direction, and that direction. They're going in every direction. We're just concerned about what happens when they're coming this direction and they hit something. So let's make them hit something. And maybe that something is a wall. And these are sound waves. Well, one thing that can happen is they can pass right through, okay? And so this wave pattern that started back in that other room just continues, and you can hear my puppies because it's coming right through a wall, right? If this was a wall and this was light, it probably wouldn't pass right through. But if this was glass, it might. One good thing that happens when you're teaching online from home is you can stop the video that you're making if something goes wrong in your house. And my puppies were getting crazy. So while just a second has gone by in your time, about half an hour has gone by in my world. I've had time to change my clothes and put my very bad puppies banished to their crates in the garage because they tore up a couch while I was doing the last segment. So we're moving on, puppy free, hopefully. And we're talking about light and sound waves, what happens to them when they interact once they go out from wherever they came from. So the next thing that could happen is they could reflect. And you have all been the subject of reflection before. You have enjoyed that, that aspect whenever you have looked in a mirror. You look and the light reflects back and you see yourself or whatever else is in the mirror. You may have also had the same thing happen with sound. If you've ever been somewhere where there's an echo, then the sound waves are going out, they're hitting something and they're bouncing back and they're coming back to your ears, and your ears are hearing them at different times, so it's echo, 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 echo. All right, so the next thing that could happen is that they're reflected, which reflection just means the waves are bouncing back. So I'm going to draw for you, let's pretend that this is a mirror. and I'll use red. Okay, red is my light ray or my sound wave coming in. Okay, so I put an arrow on it so I know it's coming from that direction. Now there's something that you may or may not know the name of, but if we drew a 90-degree angle straight up from there, we call this line the normal. And it's nothing more than a 90-degree angle at the point where that ray, or I'm sorry, not that ray, that wave hits whatever this medium is. The thing that it's hitting or going through is called the medium. All right, so let's say it's a mirror. It's going to hit at that point and it's going to bounce back up the other direction. Okay, now the really cool thing, which you probably already know because you're super smart, is it hits at some angle here. Okay, let's call it angle A. Okay, that is A is the angle of incidence. Like it's an incident that it hit the wall. Oops, an incident happened. A wave came and hit the mirror. This angle right here, although my drawing is not perfect, is called the angle of reflection. Makes sense. It's on an angle and it's the reflection because it hit the mirror. I want you to think for a minute. What do you think the relationship is between that angle, angle A, the angle where it's coming in, related to the normal, that 90-degree angle up, and the angle where it goes out, related to that normal? I'll warn you, my drawings are not perfect. If they were perfect, it might be more obvious. But think about it just for a second. You've probably come up with angle A, that angle from where it came in, the incidence up to the normal, so this area here, is equal to angle B. And as I said, my drawing is not perfect, but in real life, that is true. I'm going to show you a clip that I made last night when it was good and dark in my house, and of me trying to prove this to you with a little tool. I was using this device. You might be able to see it. It has some arrows on it, which I'll talk about in just a second, and then it has a protractor that goes all the way around, and I had some mirrors set up to the bottom. So you'll see that, and then I'll show you some better scientists doing it as well.
This is my light box. You can see my light reflecting off the mirror at the angle 40 degrees going in and 40 degrees going off. When I turn the light off and use the laser, you can see a little better that the light goes in at 40 degrees and comes out at 40 degrees.
All right, so let's think about if we had a mirror. Well, we're doing it this way. Let me get my eraser. Let's say you're standing in the bathroom and you have a mirror this way on your wall, and your eyeball is over here. Aren't you pretty? And you look, let me do my red so it matches up over there. You look straight into the mirror. Okay? What is the angle right here? You got it. It's 90 degrees. If you're looking straight in that case, your normal and your wave coming in are both the same. And so if the angle of incidence comes in at 90 degrees, then the angle of reflection has to go back at 90 degrees, and you see yourself straight on. And that's why a mirror works. If that mirror is wonky for some reason, you might see yourself distorted. That would be like if you were in a fun house, or if it was angled, you might see up to the sky. Another thing that you may know is this is how we see color. So I drew here a leaf. My leaves outside my kitchen, thankfully, are now green. You know that light has the entire spectrum of colors. All those colors are coming in. All the colors except green are being absorbed, okay? Green is being reflected back. So we see the color green because it's reflected back. So all the colors come into the leaf at whatever angle, and then the green is reflected back, and we see the green rays of light, the green light waves moving and hitting our eyes. So imagine I did an internship at the shipyard a few years ago, and let's say we're looking at a pipe that's going like this. That's a pipe, really it is, all right? And this welder over here, oh, and there's a wall right next to this pipe, okay? It would continue on. This welder needs to weld something on the back side of that pipe that is almost smack dab up against a wall. What the welders have to do is learn to put a mirror here. So this is their medium, the mirror. And then they stand out here and they have to angle the mirror, well, that's not good. They have to angle the mirror just right so that their angle of incidence in will give them the reflection to where they need to weld, and then they need to weld looking kind of backwards through a mirror. So we can use mirrors for things like that. Here's another way that we can use mirrors. Let's say you're in a submarine. Okay, here's my little submarine. That's my propeller. I don't know what that is. Okay, and we're underwater. Well, I want to know what my enemy is doing in my neighbor's backyard, but I'm underwater and I want to stay underwater because that's the whole purpose of a submarine. You may have seen submarines, they look through something called a periscope. And what a periscope is, here's the little submarine man down here, and he has a tool that's basically like a tube that goes up, okay? And he has a medium that's a mirror right here, and a medium that's a mirror right here. And now he can look in, and he has an angle of incidence that reflects off. And even though it's an angle of reflection here, at some point it becomes the angle of incidence here and reflects off to whatever he's looking at. And then the light ray bounces off whatever he's looking at, comes back, and he can see whatever he wants to see ahead of him. So that's one useful way that we use mirrors to help us. The last one I want to talk about is if we use sound waves to bounce off. So let's say this is the bottom of the ocean, and there's a deep trench in the ocean. And way up here at the surface, I'm going to get rid of my leaf. Is a ship. All right, that ship can send out sound waves. They start small and they get bigger. And finally, those sound waves hit something. And when they hit, they are going to bounce back. So now we have sound waves coming this way, back from that edge right there. And the operators on the ship know the length of time it takes for a wave to travel through water. So based on how long it takes for that to go down and come back, they can measure how far it is to this point. But remember, there are other waves too. So there's a distance right here. There's also a distance to come back right here. And so they can measure the two distances and know that this one took less time to come back, so it must be shallower, and this one took longer to come back. Oh, I forgot to hear my ones coming back. All All right, so when they hear the ones coming back from here, they took longer, so that water must be deeper. And that's called sonar. We could also do it if it was a submarine and it sent the message, the waves out to see what's ahead of it. It hits a ship and it bounces back. They know there's a ship in front of them. If it's a deep ship, they know how big a ship it is. And then you guys also know, let's say, I'm going to get rid of my water here. Okay, let's just say we have waves and we have a bat. Okay, bats use echolocation. They send out sound waves, and then when the sound waves come back, they can read it in their head. Dolphins use it also, porpoises, lots of animals use echolocation, which is basically sonar, and he knows, hey, I better not fly this direction or I'll run into something, but if I fly this way, I can go longer. Or maybe what he's actually testing is not the direction, but hey, there's the food I want to eat. I can tell the shape of the food because some lines are taking longer to get back to me than others. Same idea when you get an ultrasound of something inside your body. Here's the ultrasound tool, and it's bouncing off your liver, your kidney, or maybe a baby growing inside. And the way those sound waves come back, they put together, and you can see the depth of how deep things are. So those are some ways that we use sound, and I already mentioned echoes as well. Okay, the third thing that can happen once those waves go out from whatever created them, with the first we said they could just pass right through. The second we said they could bounce off, that's reflection. The third one is they can bend as they go through something, and that's called refraction. So refraction is the bending of waves due to a change of the speed of light in a medium. And remember, the medium is whatever they're passing through. If you notice the definitions are getting longer as we're going on, I noticed that. So let's pretend that we have a wave. We're going to spread it out. Instead of that just being the wave, we'll make it look a little more wavy, okay? We're going to pretend that we are an ant. So that looks to us like this, all right? It's not two waves, it's all one wave that's passing, that's going. I've just spread it out. And then we get to our medium. I'm going to make my medium yellow. Okay, there's my medium. Over here, my wave is passing at the speed of light. Well, imagine it's in a vacuum and nothing is impeding it. But over here in my medium, which I'm actually going to make a little bit bigger so I can write in it, there are a couple things that could happen. It could also be at the speed of light. And if that's the case, then my wave will continue to travel through it, and it will look pretty much just like it did before it started. No change in the speed that the light's traveling, so nothing's happening to it. In this case, there is no refraction. No refraction. Okay? But I'm going to erase this. We'll come back to it. Okay, a couple of wonky things can start to happen. Some optical illusions because of refraction. One, I'm sure you, almost positive, you have seen before. One, you probably have not maybe seen before. So let's imagine that we have a straw going into a container here. We just saw that if the light wave passes through a medium that has the same speed, nothing happens to it. But what if we had a straw coming into our glass, let's say, and in this case, we're traveling at a speed, whatever it is, fast or slow, we don't know yet, but it's gonna go into a medium where the speed is actually faster, okay? The rate at which the rays will be coming back is faster. Well, this is our normal right here, all right? It's the 90 degrees that it's gonna hit at. And it's going to look, because it's faster, it's coming in slow, 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 and then fast. It's going to actually look as if the straw is bent in half or bent on itself. That you probably have not seen. This, I'm thinking that you probably have. If the straw is coming in, let me draw it over here a little bit better. It's coming in at an angle, it's resting on the side of the glass, okay? And we're going at some speed here, whatever the speed of light around our eyes is. And now it goes slow, okay? So it hits water or oil where it travels at a slower rate. We're going fast, 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 and then it slows down. In that case, it's going to bend towards the normal. We would expect that the straw would look like this. That's what our eyes want to think. But it actually slows it down, and so it bends away from the normal. So instead, it ends up looking like this. And it looks like the straw has been split in piece, and there's a water straw and an air straw. You may know this if you've ever read the book Hatchet. The character is trying to fish, and he has a spear because he's been left in the woods, and he remembers from his science class, thank you, yay science, that he needs to not aim right for the fish. He needs to aim a little off from the fish, because where the fish appears is different than where the fish actually is. So that's how that optical illusion occurs, and we'll see that happening. So at the beginning I said, you might want to get a glass of water. I'm going to go get my water, and a straw or a pencil. And when you put the pencil in, you've probably done this before. It looks like a magic trick. All right? It looks like the pencil is bent. That's a sideways view of what we have happening here, because it travels at one speed through the air, and then it hits your glass of water, and it slows down. So if I could turn this sideways, which I'm not going to do because I'll have a flood, I would see why my pencil or my straw, whichever you put in, looks bent. And if we were in class, we would be doing this as a lab, but I don't have enough hands. If I put my pencil, let me get it in there first. All right, so that the top of my pencil is right at 40 degrees, then I would expect this to be right at 40 degrees too. But I'm going to grab a book and put it behind, and you probably can see that although the top of my pencil on the top half is 40 degrees, it's about 2 or 3 degrees off down at the bottom. Okay? Water and air aren't that much different. They're enough different to make it hard to catch a fish and hatch it, but water and air aren't that different. So it's not a huge change in degrees. I'm going to show you a video where a scientist who has a lot more accurate equipment than me shows you how that angle changes.
Five degrees. 10 degrees. 15 degrees. 20 degrees. 25 degrees. 30 degrees. 35 degrees.
All right, I want you to